First, I'll take a review of the set theory. So we all know that set is a collection of unique elements. Okay, so there are different ways sets are represented. One way is you can just list all elements. For example, s equal to 0, 1, 0, comma 1 in the curly braces, that means set is made of two elements 0 and 1. It can also have infinite elements like all positive set of all positive elements that will be 1, 2, 3 and dash dash dash, that will represent a set of all positive integers. Writing s equal to 0, 1 in the square bracket means it is a closed set containing all the real numbers between 0 and 1, including 0 and 1. And s equal to 0, 1 in the open parenthesis, that means it's again a set of open set containing all the real numbers between 0 and 1, but does not contain 0 and 1. The another notation would be, which we call set builder notation. In this, we do not write all the elements, but we just write the property of the elements we want to include in this set. And that is a compact notation. For example, I can say S is made from all x, where x is a natural number. So in this case, this set will be 0, 1, 2, 3, 1, 2, 3, and in this way, we don't have to write all the numbers. We just write the property, and it will be sometimes easier to write in this way. Similarly, I can say S is made from a pair x comma y. So each element is a number. Each element has two numbers, x and y, and x is equal to 2y. So all the elements which are pairs such that first element is the double of the second element, which makes this set. Right. If you can realize that writing this set, every element of the set is really difficult, but this way it is easier to understand. So the main notation here would be to put curly braces and they say x such that gx, and gx is some condition you want for the set. If a element satisfy this, then it should be in the set. And this notation should be conclusive, means you should there should not be any doubt after whether the element should be in the set or not. And then once you have defined set, then another important thing is something called power set. So power set is of a set S is a set of all subsets of S. So power set is a set of subsets, right? So each element of power set is a set, which should be the subset of S. So you can say if S is just has one element 1, then the power set would be what are the subsets of this S? There are two subsets. One is the empty set. Empty set is always the subset, and the set itself 1, that is also a subset of S. So if you make a set of these two subsets, you will get the power set. Power set is denoted by PS or 2 to power S. That is not exactly 2 to power S, it is just a notation to say it is a power set. Similarly, if S is 1, 2, there are 4 subsets possible. One is empty set, one is a set containing 1 only, one is a set containing 2 only, and the third one is a set containing both sets. So what is cardinality? So for a set S, number of elements in that set is termed as cardinality of the sets, and it is denoted by ns or this mod of S, which we call cardinality of S. And depending on whether set has finite or infinite numbers, this cardinality can be finite or infinite. For example, if you take a set 1, 2, 3, the cardinality is 3, it is a finite set. If you take Z, which is collection of all integers, they are infinite integers, so this is an infinite set and cardinality will be infinite. Now can you guess what is the cardinality of power sets? Suppose I take this set 1, 2, 3. What will be the cardinality of the power set? If you try to make subsets of this set, you will see that there are total 8 possible combination of these numbers. So there are 8 subsets possible. So the cardinality of the power set of this set would be 8. In general, if you have n elements, the cardinality will be 2 to power n. And that can be shown just by a simple combinatorics argument. Cardinality of power set is generally bigger than the cardinality of the set itself, right? Because you are including all possible subsets. Now, how do we compare the cardinality of two sets, right? So that is very easy. If they are finite set, I can just compute the cardinality and I can just say if one is bigger than the another one. So if S is 1, 2, 3 and S2 is 1, 2, I know the cardinality of S1 is 3 and another cardinality of 2 is 2, then of course the cardinality of S1 is more than cardinality of S2. And by the same argument, you can prove that for finite set, the cardinality of power set is more than cardinality of the set itself. Okay, you can simply say that if there are n elements, and if you try to write down the subsets, you can always form subsets by taking only one element at one time. So there will be, of course, n elements and subsets possible, but there can be more subsets also. So the cardinality of power sets, which is the number of all subsets, is more than the number of elements in the set. Now the question is, this is okay for the finite set. Can we also compare infinite sets, right? For example, if I say Z, which is the set of all integers, this also contains negative and positive all numbers, -2, -1, 0, 1, 2, 3. Is it bigger than the natural number set, which contains 1, 2, 3, 4? Right? Or is the set of natural numbers bigger than the set of even numbers? Right? You can say, for example, even positive numbers. So natural number is 1, 2, 3, 4, 5, and the even numbers only contain 2, 4, 6, 8. So what do you think? Some can say that natural numbers has more numbers because it also has 1, 3, 5, which are missing in the set of even numbers. And some say both are infinite number elements, so they should have the same cardinality. So to apply that, what we do is we pick one number from the first set, pick another number from the second set, put them together, and we keep on doing it until one set exhausts. Okay, this example works for the finite set, right? If you take one example from A and B and you put them together, then you take another element from A and another element from B and put them together. And if B exhausts, B becomes empty first, then A is bigger. This kind of argument can also work for infinite sets, where we do side-by-side comparison of two sets. Here the cardinality of two sets, we will require mapping. And mapping can be done via functions. So I'll review functions shortly. A function is a mapping from one set to another set. It means you can map elements of one set to another set. Now suppose there are two sets A and B, then formally we can define function in the following way. A function is, f is a function from A to B, f from which we denote as f colon A to B, if every element of A should be mapped, right? This means all the elements of A, capital A, there should be a mapping to B. And if there is any element left in A which does not have a map in B, then it will not be a function. Mathematically, we can write it in the following way. Small a belongs to A implies that there exists a B in capital B such that small b is equal to f of small a. Right. So mathematically, we also need to understand these kind of statements because in this course we will be writing in mathematical language also. So A implies B means if A is true, B should be true. It doesn't say anything in the backward direction. It means if B is true, I do not know what happens with A. But A implies B means if A statement is true, then B statement should be true. So here it means that the first statement is A, small a is an element of capital A. It means if there is an A which is element of capital A, then there should be a B, small b, in a capital B set such that B is equal to f of A, means B is a map of A under this function. And the second condition which would be is that unique pair in B means every A should be mapped to only one B. Okay, so this can be mathematically written as if B is equal to FA and B dash is equal to FA, then B should be equal to B dash. It means if there are two elements B and B dash which are both mapped from FA from A, then they should be equal. Okay, and then we also talk about domain and codomain. A is called domain and B is called codomain of this function. Now, instead of writing, how can we represent functions? So you may have seen that we can just write fx equal to 2x. In that way, we are basically defining the properties of this function, saying that every x is mapped to element 2x. Sometimes function can also be written as the set of ordered pairs where you write. So every mapping is a map from one element of capital A to another element of capital B. Right. If we write down all these pairing and make a set, then that will also represent function fully. So function can also be seen as a set of ordered pairs A comma B such that B is equal to FA. So we can take another example. Suppose capital A has two elements, A1 is three elements, A1, A2, A3, and capital B has two elements, B1 and B2, and they are mapped in the way that A1 is mapped to B1, and A2 and A3 both are mapped to B2. This is a valid function. You can verify using the formal definition of function that both two conditions are being satisfied. Then you can represent this function also in the following pair that there are three maps, A1 to B1, A2 to B2, and A3 to B2. So it will be a set of three pairs. Now what is image of a set? So suppose C is a subset of A, then the image of C under this function is the set of all elements which are mapped in B, which are mapped from any element of C. So formally we can write this. We denote it by F square bracket C. This is image of C under function F is equal to set of all FA such that A belongs to C. So you take every A in C and you calculate the map FA and you make the set and that will be your FC. Okay. If suppose all element of A are mapped to the same value, then it will have one element. And if they are mapped to a different element, then it will may have similar number of elements as A. As C. So this is, in short, the set of function values at all elements in A. Similarly, we define pre-image. So what is pre-image or inverse image of D? So D is a subset of B, and it is made, the pre-image of D is made from all elements which map to a element in D. Okay, so F, which we call F inverse, F to the power minus 1D, that is the pre-image of D, is made of all elements A, such that A belongs to A, capital A. So A need to be element of the domain, and the map of A, which is FA, should be in D. So set of all elements in A whose pair, whose map lies in D, right, or whose pair lies in D. Now, the important thing to notice is that there may be some elements in D which does not have a map, right? So we never said that all elements of B need to be mapped. We only say all elements of A need to be mapped, and there can be some element left in B. So D is a subset of B, so there may be some element left in D also. We don't care about that. Find out all the elements which has an image, in which has a map in A, and collect those. So basically you have to collect all A such that they map to one element in D. Okay. So what kind of functions we can have, right? Let us see this image. There are 4 different configurations I have talked about, right? So first, if you look at one in the top left, you can see that it has 4 elements in capital A and 4 elements in capital B. So blue one is set A and red one is set B. And in this case, you can see that every element of A is mapped to B. Okay, and one element of A is not mapped to 2 elements of B. Okay, so it is a function. Now there is one additional condition which is being satisfied, that every element of set B is also covered. It is mapped from A, and every element of B is also uniquely paired with A. It means the A in first set is not mapped to 2 elements. Each A is mapped to a distinct element in B. Now, if you look at the second one, uh, top right one, it has 3 elements in first set and 4 elements in the second set, and it is also one-to-one unique map, but one element of B is not covered. The third set, if you look at, which is bottom left, it has 3 elements in first set and 2 elements in the second set. This is also a function, but there are cases where 2 elements of first set are mapped to the same element in the second set, which is red. Now, if you look at the fourth example, in this case, this is not a function itself, because the second element in the blue set is mapped to 2 elements of in the red set. So this is not even a function. So based on these scenarios, we can have some classification of function. First function which we discuss is, they are called one-to-one functions, or another word is also injective functions, which means functions where no 2 elements of A are mapped to the single element of B, right? So remember again, functions, just saying function, it allows that 2 elements of A can be mapped to the same element of B. Okay, but one-to-one function has this additional condition that every element of A should be mapped to a unique element of B. Mathematically, we can write in the following way, that if there are 2 A1 and A2 which belongs to A, and for both FA1 and FA2 both are equal to B1, then A1 should be equal to A2, because two elements distinctly cannot uh, map to the same element. So they need to be equal. So out of these four cases, you can see the top two cases are one-to-one injective functions, because every element of in the red set is distinctly mapped with the blue set. Now let's take another class of function, which we call onto or surjective function. So onto, as name says, it's like on the B. So every element of the set B should be covered. Okay. So normally in functions, some elements of B can be left out. But here we are making an additional condition that onto functions are those functions where every element of B is mapped. So there are no element in B left. So mathematically we can say that for all B, small b in capital set B, there exists one A which such that FA is equal to B, or in simple words we can say that for no matter what element you take in capital B, we should be always able to find a element in capital A such that A is mapped to B under this function. So if you look at these four examples, the left two are onto functions. Okay, and of course the right ones and the top one, you can see the function, there is one element left, and the bottom one is not even a function. Now combining this onto function and one-to-one function, there is one class which is called bijective functions. These are functions which are both one-to-one and onto. Okay, so this means that all element of B should be covered, and also every element of B should be uniquely paired with A. Okay, and from function definition, you already know that every element of A should be covered and every element of A should be uniquely mapped. Right. So bijective functions are those functions where both set A and B are covered. It means every element of A is mapped to B and every element of B is mapped to A. And also every element of A is mapped to a unique element in B, and every element of B is mapped to a unique element in A. Okay, so that's why we call it one-to-one correspondence. If there is a bijective function between A to B, means all elements, there is a one-to-one correspondent. For every element, there is a unique image and also a pre-image. Now we come back to the comparison of cardinalities of two sets. So with this function mapping, we can say the following. At least you can understand it for the discrete case very easily. For finite sets very easily. That if there is a bijective mapping between two sets A and B, then they must have same number of elements, right? So basically, this means every element of A and B are covered, and every element of A is mapped uniquely to a element in B, and every element of B is uniquely mapped to an element in A. This means both there is one-to-one correspondence. Both should have the same number of elements. Okay, if anyone has less, then it should not be able to map them uniquely. And for finite case, this should be easy, right? And then of course we can also say if there is an injection from A to B, right? This means for every element of B is uniquely mapped to an element in A. Okay, now you can understand if A has more elements, right, then there would be cases where two elements of A are mapped to the same element of B, right? Because every element of A has to be mapped. And if A has more element than B, then there would be one case where two elements of A is mapped to the single element in B, right? So this means that if there is an injection, if there is a unique map of every element of B in A, then B need to have more elements or at least equal elements than A. Right? Why we say more? Because of course there is a possibility that we can leave out some elements in B. So B can have more elements than A, but not less. Top with that, if we say there is no surjective function from A to B, it means if you are not able to find any function f which can cover every element in B from A, right? It means B need to have more elements than A, right? If they are equal, then of course you can find one-to-one map, right? And that will be of course surjective also, right? Right, you can find one bijective mat from A to B if they are equal, and of course that will be surjective. So but if you're not able to find any surjective, it means no matter what function you find or try, it's not possible to cover every element of B. It means B then has strictly more elements than A. Now these statements are also true for infinite sets, right? If you have two infinite sets and you can find a bijective mapping between them, then we say that both have same cardinalities, right? And it's look intuitive, right? If you have two sets and they are one-to-one map to each other, right? You can count them, you can take one element of one set and another element of another set, and you keep on picking these two elements in one by one from both two sets, and you're always able to find a pair, right? And none of the set runs out. It means both have same amount of uh, same number of elements. Okay, and rest two are also in the same way. So let's see an example for infinite cases. Let's say capital A is a set of positive integers. It is made from all the integers which are positive. And B is a set of even positive integers. Mean it is only made in such a way that it is made from x such that x is equal to 2y, where y is an integer. And of course, x need to be positive. Now, do they have same number of elements? Someone says A has 1, 2, 3, 4, and B only has 2, 4, 6. So it looks like B is smaller. But that is not the case. You can see, you can take one element of A1, and then you can map to 2. Then you can take 2 and map to 4. You can take 3 and map to 6. So you take any elements in N, and then you can map to 2n in B. Right? It is a bijection map. Why? Because you take any element in B, and that is you have a map, right? So for example, you take 100, it is mapped to 50. You take any element, you can find, because it's all even numbers, right? So using this map x equal to 2y, right, or let's say b equal to 2a, this map you can always take 1b and you are always able to find 1a, because b is a even positive number. So you can always find 1a which is a positive integer. Okay. Similarly, they are unique also, because if you take b by 2 is a unique element, right? And of course this is a function. So you have a bijection function specifically said as f is equal to b, fa is equal to b is equal to 2a, right? And that way you can always cover all the elements, and this is the bijection map. So we say that A and B have same cardinality, right? Although both are infinite sets, still they have same cardinality. Okay, and of course their cardinality will be infinite, right? But we will see that even there are different infinite sets which may have different cardinality, right? So the cardinality of A and B in this example, both are infinite and they are equal. So they are same type of infinite cardinality. Okay, and of course you can also see this point that in this case A is a B is a subset of it, right? So even then it is not necessary that cardinality of B is less than cardinality of A. So finite set, this is true. If you take a subset, proper subset of another set, your cardinality decreases. But this is not true for infinite sets. Right. Let's take one more example. X is a positive integer, and that is A, and B is made from all integers. Right. You can prove that they also have same cardinality. Right. Although A is a subset of B here, B looks like to have more elements. A is less than B. Sorry, A is subset B. Still, cardinality of A is equal to cardinality of B. And how? Of course, to prove this, you need to find one bijective map which maps A to B. Right. So this is very easy. One example is said here. Right. It's mathematically written as if A is odd, map A to A plus 1 by 2, and if A is even, map it to minus A by 2 plus 1. Okay, so this means 1 is mapped to 1, and then 2 is mapped to 0, 3 is mapped to 2, 4 is mapped to minus 1. So you take one element in B, 1, 2, 3, 4, sorry, one element in A, and then you, if it is odd, map to the positive side, and if it is even, map to the negative integer, right? And this way you can map every positive element to one integer. Okay, right, let me say it again. So you have in A you have only positive integers, and you want to map these positive integers to every integer. So what you do is you take odd integers, odd positive integers, and map to their half in the positive side, and then you take you take even integers and map it to every integer in the uh, negative real direction. Okay, so you can show by using this, you can prove that using this function you can cover every integer. So I said that there may be the two sets may have infinite cardinality, but there are different types of infinite cardinality also. So from this, a relatable concept comes, which is called countability. Right? So what is countable? As a word say, something which you can count is countable. So what can you count? Finite sets, yes. So if you have a finite set, you can take this element and count how many elements are there. 1, 2, 3, 4, right? This is like basic act of counting. Like you start with 1, 2, 3, 4, like this. Right. So what is exactly used for counting, right? You have seen you can count via hand, right? But the basic fundamental thing is that you need numbers to count, right? 1, 2, 3, 4. And that is where this concept of natural number comes. Natural numbers are the numbers which are used for counting. They start with 1, 2, 3, 4 like this. They are infinite, right? So that you never runs out of the number, and they are countable, right? That is where this word is coming. They are countable infinite, right? So what other sets have countability? You can say any set where you can find a bijection map with the natural number set is countable, right? Why does bijection? It means you are able to map every element of that set with one element of natural number. Right. So suppose there is a set with numbers, suppose A, B, C, D like this, and then you map one number to 1, another number to 2 and 3 and 4, and this is like a bijection from natural numbers. So every element of that set is mapped from one number of natural number set, and then you can say that element is that number. So suppose it is mapped to 1, so I'll get this is the first number. If the number is mapped to the sixth element, it's the sixth number, we call it the sixth element. If it is mapped to n, then we call it nth element. So that is why you are able to find an order in the set, right? And you are able to count them, that this is the first set which is mapped to the number 1, this is the second element which is mapped to 2, this is the nth element which is mapped to n, right? And if you can find a bijection map, this basically means that you are able to put an order in the set and you are able to count the elements of that set. And that is why we are saying that set is countable. So any set that has bijection with natural number set is countable. We say its cardinality is countable infinity. Okay, and of course natural number also has this countable infinity cardinality, and that is why, because you are able to find a bijection between these two sets, so both sets have same cardinality, and that cardinality is known as countable infinity. Okay, and this is written by this particular notation. Okay, this is called LF0. This means it's a countable infinity. Now, so what other sets can be there? Set of positive numbers, positive integers, set of negative integers, set of even element, or set even integers, or set of integer divisible by 3. For each case, you can find a bijection which natural number set, and you can prove both have same cardinality. So the set should have a countable infinity cardinality, and that's why the set is countable. Okay, so you can try take a set which is made from integer divisible by 5 and prove that there is a bijection between natural number and this, which means you are able to map each element of natural number to a unique element in this set, and of course each element of this set uniquely to a natural number. Right. What other results we can prove? One more example I'll take. Suppose A and B are both countably infinite, then I want to say the union of A and B is also countably infinite. What is the example? Suppose you take negative integers and you take non-negative integers. Both are countable infinite, and then you take a union, so you get all the integers. And I want to say the integer set is also countable infinite. So how can we prove this? Let's take an example of this. So to show this, we can do the following. First, let's take set A and B, right? And they have some elements. Right? I do not know what are the elements. They can be words or something. But whatever elements are there, because they are countable, I have assumed A and B both are countable, you should be able to order them and map every element to one natural number. So this should be 1, this should be 2, right? And the order can be, of course, different, but I am reordering the elements in order of 1, 2, 3, 4, because you're able to find a bijection. By saying A is countable, you're able to find a bijection, means you're able to map every element from one natural number uniquely, right? So after you found the map, you reorder in this 1 to 3 order. Similarly, B also you are able to map 2 and 3 like this. So every element is ordered, right? Now you have, say there is a 1 union B, right? And this is made from the union of elements from A and B, right? Let's assume A and B are disjoint for simplicity, and you collect all those elements, right? And you make this element, right? Now, how can we assign order to this, or how are able to find one bijection from this, right? So 1, 2, 3 like this. This is your order, and you're should be able to assign elements here 1, 2, 3, and 4, such that all elements of A union B are covered and in this order, right? So this is rather easy, right? We can do the same way for every odd number. right? For every odd number, pick one element of A one by one. So here I will put A1, right? First element of A, right? First element of A means the element of A which is mapped to 1 in the original counting of A. Similarly, in 3, I will map to A2. In 5, I will map A3, and that's why I will cover all elements of A1, A2, A3. Similarly, in the second spot, I will map B1, the first element of B, second element of B in 4, and like this. Right. So this is my bijection map. I am saying this is a bijection which requires some proving, although it's intuitive to understand why this is a bijection map. And you're able to map every element, right? So if you're able to map every element of A union B to a natural number set, then this and this set has same cardinality. This means A union B is also countable infinite. Okay, now how some arguments are still left. For example, I can formally write this using the same map, right? So the map I have to say, if I take the sixth element of A6 in this A union B, then where should we map it, right? So you will say if you take any element of A6, that will be at the position of 12. And if you take any element of B, it should be on the 12 plus 1. Right. So the order would be, if you give AN, it should be at 2n location. It's mapped to 2n. And if you give me BN, it should be mapped to 2n plus 1. Right. So this is like a for mathematical formula for form. And then you can see from looking at this, you can say I am able to map every element of A union B, because every element of A union B would be either from AN and BN, right? If I can find out which set this belongs to, I find the order original where it was in the set. From that n, I am able to map it to 2n. If it is in B, then it will be mapped to 2n plus 1. Okay, and because 2n and 2n plus 1, these set are made from even and odd integers, so it also exhaustively use natural number set. There are no number in natural number set are left which are not covered under this 2n and 2n plus 1 form. Okay, so so I can ask the reverse question also. You have proven that every element of A union B is mapped to one natural number. How can you inverse it? If I give you a natural number, can you map it back to A union B? And that's also very easy. If the number is if the natural number gives me is an even number, then you map it to A n by 2. And if it's an odd number, then you map it to B n minus 1 by 2. So similarly, if you take 13, it's an odd number. So you do 13 minus 1, 12 by 2, 6. So you map to B6. Okay. And so you are able to prove that this is a bijection, and every element of A union B is you can find a number, and every number in natural number set you can find a number in A union A element in A union B. No element in natural number is left. No number in A union element in A union B is left. It's a bijection. So A union B should have same cardinality as natural numbers. So both are countably infinite. Now let's see one more example. What other sets can be countably infinite? So integers are countably infinite, even integers, odd integers, these are. Okay. So another interesting countable infinite set is a n cross n, right? So what is a cross notation? You know, A cross B is a Cartesian product of A and B, and that is made from all pairs or from where one element is taken from A and another element is taken from B. So if you have suppose 1 comma 2 in one set and 3 comma 4 in another set, you take all combination 1 to 3, 1 to 4, 2 to 3 and 2 to 4. So there will be 4 combination. So A cross B will be made from 1 comma 3, that is one element, 1 comma 4, 2 comma 3 and 2 comma 4. So n cross n is made from is a set of all pairs uh, where one element is n and another element is also from n, right? So what can be the elements? They can be 1 comma 1, 1 comma 2, 1 comma 3, like this, 1 comma n and up to infinite. Then you take the second element of first set 2, and then you take all elements of second set n. So this will be 2 comma 1, 2 comma 2, 2 comma 3. Similarly 3 comma 1, 3 comma 3. So it is infinite both in the horizontal and the vertical direction. Right, this looks like a bigger set than natural numbers, right? But we and this is like a 2D grid, right? If you make a x and y axis and you make all the grid points, that's how this looks like. Now the question is this countable infinite, right? And for this we of course have to prove that there is a ordering of this. Now the problem is if you start ordering in the horizontal direction, you get 1 and the second set is 2 and the third is 3, and that's how you go to infinite. You don't even know where 2 comma 1, what order you give to 2 comma 1, right? And that is the first thing in this bijection map. When you say I have found a bijection map, you should be able to answer questions like, if I give you an element, can you tell me the order, right? What is the number it is assigned to? So if we say I try to count in a horizontal direction, people will say, okay, you have found a bijection map, tell me what is the number assigned to 2 comma 1, right? And this will be a problem because you you will need infinite number even covering one line. Okay, and the other question people ask that if I give you a natural number, can you tell me which number, which pair it is assigned to, which element it is assigned to? Should be able to. So just remember, even in exams, and normally when you say you have found a bijection map, you either write it in a mathematical form that this is the exact bijection map. You take one n and this is the pair it maps to, or you should be able to tell exactly how, given a number, I will find the element as a map to, or if someone gives you an element, I should be able to tell by a simple calculation or by a formula what number it maps to. Okay, so to map this, there is a famous diagonal counting trick, right, which can count the elements, and then you are able to tell exactly which number it is assigned to. Okay, so let's see that case. So here, let me write the complete set n cross n. And it is made from 1 comma 1, 1 comma 2, 1 comma 3 up to infinite in this direction, 2 comma 1, 2 comma 2, 2 comma 3 like this, 3 comma 1, 4 comma 1 like this. So the way I start numbering this is I'll call this 1, then this will be 2, and then this will be 3. Okay, and again come back to this will be 4, 5, 6, then 7, 8, 9 and 10, right? So the order you are going to follow is like this, and then once you exhaust 2 diagonal, then you come back and again, and then you come again. So one there will be 1 element, in the second there will be 2 elements, in the third there will be 3 elements, then there will be 4 elements. Okay, so now if someone asks you 2 comma 1, you are able to tell it's a 2 number, right? Also, you can give it a mathematical form also, right? You have to form, you have to basically tell that if there is a pair P comma Q, where would I assign? So this is a set number from n cross n. If someone gives you that number, you should be able to tell where does it map, right? So you know it is mapped to the first in the grid, it is at the pth row and the qth column. Okay. Now you can observe here, first there is a one element, then there is two element, right? So the first row, first element, right? So first you have to find in PQ which column it would be, right? In the diagonal. So this, if I, so this is in the original grid. In the counting grid, this is the first row, this is the second row, this is the third row, this is the fourth. So you can observe here in this diagonal counting that in the counting grid, this I am calling as counting grid. Okay, just for sure, this is counting grid, and this is original grid, right? So in the counting grid, the rows are such that every element has the same number as the summation. So in the first, you can see 1, 1, it has 1 plus 1, 2. Okay. In the second row, it is 2 comma 1 and 1 comma 2. So both sum to 3. Okay. Similarly, the third row, both sum to 4. Sorry, all three elements sum to 4. 3 comma 1, 2 comma 2, and 1 comma 3. They are all sum to 4. Then at the fourth column, they all sum to 5, right? 4 comma 1, 3 comma 2, they all sum to 5. So one thing you can notice that in any counting grid I, the elements is made from the elements pairs such that the summation of the two element is made from xy such that summation of the two elements x plus y is actually equal to I plus 1, right? So if I is 1, it's made from elements which sum to 2. If I is 2, means second counting row, it is made from all the elements which adds to 3. So this is counting row I, and it is made from all elements xy such that x plus y is equal to I plus 1. Okay, so now you can know if someone gives you PQ, you know that its sum is P plus Q, so it should be in the P plus Q minus I ith row. PQ plus Q minus 1th row of the counting grid. Okay, and which element it would be? So you can say this row again will start from second element from 1, and then the second element will keep on increasing from 1 to something like this. So the qth will be the qth element in this row. In this counting row, it will be the qth element. So now you have found that if you give me PQ, it should be in the P plus Q minus 1th row, and it should be the qth element in that counting row, in the counting grid, right? Now the remaining is still to find out the exact number. Okay, so let me erase the row part, because now I know that it is in this row and the qth element in the counting. Okay, now you have to just find the absolute number, which is very easy to know, because you know first row has one element, second row has two element, right? So any nth row has 1 plus 2 up to n minus 1th elements. I meant nth row, n minus 1th row has n minus 1th one element, and of course n row has n elements, right? But what is the starting index of this row? The starting index of this nth row would be as if you have counted all those previous rows. So there are total 1 plus 2 elements in the second row, 3 elements in the third row, up to n minus 1 elements in the third row. Okay, and this comes out to be equal to n minus 1 into n by 2. Right, this is the formula. And then this many elements are before the nth row. So the first element of nth row would be this number n minus 1 upon n by 2 plus 1. Okay, and what will be the qth element? Of course, the qth element of this row would be this plus q. Okay, and what is the value of n? The value of n is given here. This is the row you are interested in. So if you put this value back here, you are able to find exact number which you would assign to p comma q. Okay, so that is why you can say I found a bijection map, because you give me one element of p comma q, I will tell which row it is, which number it is assigned to, which number, natural number it is mapped. Okay, and I can tell it do this for any pq, so all pqs are covered. Now the reverse question can be asked: if I give you a natural number, can you tell me which pair it is assigned to? Right? And that's also can be done in a similar way, right? If I give you a number, you first find out from this calculation which counting row it belongs to, right? Suppose you get so you here, you know, it is 1 2 3 4 5 6. So if you are given 5, it belongs to third counting. Okay, and from that you can guess which number it belongs to. So once you know the row and the row and the column number of the counting grid, you are able to exactly tell which number it belongs to. Okay, from this calculation itself. Okay, so if you know the row number, you know the total sum, and if you know the second element, the column number, you know the second element. So first number you can find out because you know the sum of the two elements, the second number in the pair. So that's why we can say n cross n is also has the same countability as the natural number set. Now let's come back to one more example. We say the q is also countable. So what is q? Q is a set of rational numbers, and somehow q is a subset of n cross n, right? Because rational numbers can be written as a pair of numerator and denominator, right? So for example, 1 by 2 is nothing but 1 comma 2. Q is a set of any rational number, and so every rational number is like p comma by q, so it can be represented in the form of p comma q, right? So it's a subset of n cross n because every rational number is can be written as a pair of two natural numbers p comma q. Okay, why I'm saying subsets? Because some pairs you have to exclude because they map to the same number, right? For example, 1 comma 2 and 2 comma 4, both are pairs in n cross n, but they both map to the same rational number 1 comma 2. So q is actually officially can be written as a subset of n cross n. Now someone asks you what is the cardinality of Q. Okay, so it can be shown, either you can find the exact map, or there is one easy way also, where we can use two arguments, right? First, we will show that there exists injection from N to Q, right? So injection means you are able to map every natural number to a rational number, right? But of course, there is not like you're not mapping one natural number to two rational numbers. You're mapping it to unique number, but some elements in Q can be left. That's an injection map, right? So one example would be you take n and you map to n by n plus 1. Right. So if you take any n and you can map to n by n plus 1, that's a unique number. One n cannot be mapped to two rational numbers cannot be mapped to same n. Right. So in this function, you can find this is injection from n to q. Right. So from the result, we know that if you're able to find an injection, it means Q should have at least as many elements as N. Okay, because you're able to map some natural numbers to some all rational numbers to some rational numbers, there may be some rational number left, right? But because we have done the unique mapping, there should be at least those many rational numbers in Q as many natural numbers in N. So the cardinality of Q is more than or equal to cardinality of N. Okay, so that we have shown at least that cardinality of Q should be more than cardinality of N, right? It's a very intuitive thing to understand, right? You are able to map every natural numbers to one unique rational number. So of course there should be more rational numbers, or at least equal than natural numbers. There cannot be less rational numbers than the natural numbers. So that is why we say the set of rational numbers is more than the set of natural numbers. Now we also show that there is an injection from Q to N comma N, right? And the same argument you can use. You can take any Q and represent in terms of pair P comma Q, and that will be one element in N cross N, right? So that's a unique pair. For every rational number, there is a unique pair. Okay. You're not mapping one pair to one rational number, two rational numbers to same pair, right? Every rational number will have a different pair, right? That is clear, right? Because every rational number has a unique set of PQ, so it's a different pair. But of course, there will be some pairs in N cross N will be left, right? And the example will of course include for example, if you take 1 by 2, you will map to 1 comma 2, right? So 2 comma 4, 3 comma 6, such kind of pairs are left. So it's not a surjective map, it's not a bijection exactly, but this is an injection from Q to N cross N. Sure, you are able to map every rational number to one element in N cross N. So again, we can say N cross N should have more element or equal element than Q. It cannot have less elements than Q. So again, in other way, cardinality of N cross N is more than cardinality of Q. Right. Now we can finish this argument by saying cardinality of N cross N is more than cardinality of Q, which is more than cardinality of N, right? While cardinality of N and cardinality of N cross N are both same, right? So because Q is between N cross N cardinality and N cardinality, and these two are equal, Q should also be equal to N cardinality of N, right? So if a number is between A and B and both A and B are equal, the number should be equal to A. Okay, so this proves that Q, the set of all rational numbers, is also countable. Okay, so it's a little bit against the intuition normal that some say there are so many rational numbers than the integers, but they are both countable infinite. They both have same cardinality because you are able to count rational numbers. So you are able to assign one natural number to each rational number. So they have a same cardinality.